All right. So that's what I want to say regarding this this gradient descent methodology. So next one I want to mention is something like this. So right now I want to say something about this loss function. So I mentioned that right now I'm using MSE, the mean squared error, as a loss function. So there's a advantage and disadvantage mean MSE. So disadvantage of MSE, advantage is very nice, right? Because it's a quadratic function, and the gradient of that becomes a linear terms. So that is very easy to implement. And however, there's disadvantage of the mean squared error loss function is that it's very sensitive to outliers. So what I mean is this. In these examples here, in the case of a simple linear regression, suppose you only have one input features here, you want to fit a line to these collections of training data sets here. And in this case here, you might want to fit a line to be this case here, right? So that would be, seems like a reasonable fit. But now suppose within your data set, you have one outlier and located in further away from the cloud of the data sets here. Suppose your outlier is here. The question you want to see, how does this one single outlier impact the final optimal parameters of this learning curves, the optimize the lines here? So, you know, if you imagine now, if this single parameter significantly shifts the line here, you can see this methodology will be very sensitive to this outlier here. Well, this is indeed the case if you are choosing MSE as your loss function. So let me illustrate it here. So this is the best fit to this in the collection of the training data sets. So now if you introduce one outlier here, and because you're taking square of the difference here, this is 16 here. This area is 16, take a square of that. That's a big penalty you impose along on the loss function. As a result of that, your loss function will force to compensate that by shifting these curves downward. So that's what happens here. So now if you consider this outlier here, the best fit will be this one here, right? You can see now this fit here doesn't seem like good fit. It's strongly biased by this outlier here. So on the other hand, you can choose some other types of this loss function. For instance, one type of loss function is this. Instead of taking the squared loss, you may just simply take the mean absolute errors. So instead of taking square of that, you say summations of absolute values of the error residuals here. So that will be somewhat alternative ways of determining the loss function. This is something called L1 loss functions here. So if you're using L1 loss function here, let's see how does this choice of loss function and sensitive to the outlier here. So this is within this training data set, this is the best line fit based on optimizing this loss function. So now, if you have this new outlier here, you can see that, well, it didn't really change that much of the fit, of the line fit to the entire cloud here. The reason is this, because you are taking the absolute values instead of the square values of that, you penalize less on the loss imposed by this single outlier here. And which means that your algorithm still focus on optimize the loss with respect to the big cloud of them instead of the sensitive versus the individual outliers. You can see in that case, if you are using this loss function, would be kind of more, it's kind of somewhat better in this type of situation, less sensitive to this outlier here. And of course, there are many other versions of the loss function that people have proposed for regressions of that. So right now I talked about this MSE, and the other one is called absolute values, absolute errors of that. This is called L1 base. And you can also take something in between here, make it smooth but it locally look like the MAE, but globally and more closer is less sensitive to the outliers. If you propose something like blue ones here, and that will be even less sensitive to the outliers. So you have over the history proposed many different versions of that. So of course, nowadays still the first two is still the most popular ones for the regression problem. But sometimes you can think about if your data has many outliers, you may want to think about alternative versions of the loss functions. All right, so that's what I want to say regarding this linear regression today. So next time I'm going to talk about how do we extend the features to include some nonlinear features so that we can have of nonlinear predictions instead of linear predictions